Hi, everybody. Welcome back. So, this is our fourth session of chemical kinetics. And the topic that we are going to learn today is kinetics of zero order reactions. Please note down the heading kinetics of zero order reactions. Before we begin, just let's quickly brush up through whatever we have discussed in the last three sessions. So in session one, we discussed that any chemical reaction for which we have to apply the laws, for which we have to apply the principle of chemical kinetics, it should proceed with a moderate speed. Also, if any reaction is given to you, we can just look at the reaction and we can write the expression for the rate of the reaction, which involves the reciprocal of stoichiometric coefficients. The stoichiometric coefficient is only involved if the rate of the reaction is asked. Instead, if rate of disappearance of the reactants or if rates of appearances of the products are asked, stoichiometric coefficients are not considered. Okay, so this is something that we learned in the first session, and we also discussed that always the rate of the reaction, or whether it is rate of disappearance or appearance, it is always positive. Always positive. So in order to make it positive, whenever you consider the reactants, you add a negative sign. Yeah. So these expressions you write down by just looking at the reaction, and hence whatever expression that you get over here is the theoretical rate. Is the theoretical rate. Because you can just look at the reaction and you can write down the expression. Right? Now in session 2, we discussed about law of mass action. We said that the rate cannot be theoretically determined over here. Instead, over here, it is experimentally written. So this is experimental rate. So in day 1, we discussed about theoretical rate. On day 2, we have discussed about experimental rate. We said that rate of the reaction is proportional to the active masses raised to some powers. If the powers are equal to the stoichiometric coefficients of the respective reactants, then those reactions are called simple reactions or elementary reactions, where the order, which is the sum of the powers, are equal to the molecularity. While there are reactions where the sum of the powers won't be equal to the sum of the coefficients, and such reactions are complex reactions, which we'll be discussing in detail in part 2 of chemical kinetics. All right. Now, whatever proportionality sign is over here, we eliminate that by adding a proportionality constant. And that proportionality constant is called a rate constant, velocity constant, specific rates are some of the common names given to the small letter k. Now on day 3 or session 3, we discussed about the different units of rate constant, and this is the general formula, where n is the order of the reaction. Now, order of the reaction can either be positive, it can be negative, it can be zero, and it can be fractional as well. So this is where we have stopped our discussion. I want every one of you to have a summary chart like this, which will be very helpful for you for revision. Okay, you can either write it down on a few sheets of A4 size papers and then you can clip it, or you can keep a separate 100 pages notebook for that, just for the summary. Okay, so this is what we have discussed. Now, let's start with the kinetics of different order reactions. And today we'll be beginning with kinetics of zero order reactions. Kinetics of zero order reactions. Now, we all know what is a zero order reaction by now. What does that mean? Here, it means that when you calculate the rate of the reaction, it is independent of the concentration of the reactant, right? Rate, for example, if I have some reaction where A becomes P product, the rate expression will be written as will be written as rate is proportional to concentration of the reactant, which is A over here, raised to 0. Now, if I have to remove the proportionality constant, it is going to be rate is equal to rate constant into concentration of A to the power 0. Why? Because the order n is equal to 0. Now, any number raised to 0 is 1. So, rate is equal to K. Rate is equal to rate constant. That's all. Okay, if you want to write it down in words, please write it down. For a zero order reaction, for n is equal to 0, which means a zero order reaction, the rate of the reaction, ROR, rate of the reaction does not change with concentration of the reactant. Correct? It is independent upon the concentration of the reactant. What are the typical examples? One example we had already written in our previous session. Let's say you combine H2 plus Cl2. H2 plus Cl2, in the presence of photons, it becomes 2HCl. The rate expression is rate constant into concentration of H2 to the power 0, concentration of Cl2 to the power 0. It does not depend upon the concentration of the reactants. Another very famous example is reverse Haber's process. Reverse Haber's process. Haber's process is a process where N2 and H2 combines together to form ammonia. So reverse Haber's means it will be the ulta, the opposite. Reverse Haber's process. Reverse Haber's process. Okay, here also the rate does not depend upon the concentration of ammonia. It's like this. So such reactions where the rate of the reaction does not depend upon the concentration of the reactants are called zero order reactions. Now from today onwards, we will slowly incorporate graphs also in our studies, okay? We have to be well equipped in interpreting the graphs. So slowly, once you have understood the concept, it will be very easy to draw the graphs, to interpret the graphs, and also to answer our questions, which has got graphical concepts in it. Okay, so based on this, if I ask you to plot a graph between rate versus concentration, I have to plot a graph between rate versus concentration of the reactant. What you have over here is A. Right? This is what I want to plot. Let's see. Okay. So whenever I say rate versus concentration of A, or if I say Y versus X, whoever it is. So the first one, which is written over here, the first parameter comes along the y-axis and the second one comes along the x-axis. Okay, so if it is rate versus A, R comes along the y-axis, the rate, and the concentration of A comes along the x-axis. Now, what is given? It is given that, or we already know that it's a zero order reaction. And even if your concentration increases or decreases, whatever happens to the concentration of the reactant, our rate does not change. It remains a constant. If it has got a value of 10 moles per liter per second, it will remain the same. Correct? So how will the graph look like? It will be a straight line parallel to the x-axis. I hope you're getting the concept. So let's say this has got a value, whatever value it is, it's not changing with concentration. See, concentration is increasing, but the value of R, the value of the rate of the reaction is not changing, it's constant. So this is how we plot graphs based on whatever concepts that we know. Okay? Next one. What if I ask you to plot the rate of the reaction versus time? Versus time. Okay, so I have rate, I have time along x-axis. Now we do know that any process that you take, as the reaction proceeds, for example, what I have taken over here is A becomes P, correct? Now initially at time t is equal to 0, let's say I had 10 units of A and my product is 0 because our reaction has not started. After a while, after 1 minute, let's say 10 has become 8. So the product we have got is 2 units. Then after 2 minutes, it has become 6. This will become 3. After 3 minutes, this will become 4 and this will become 6 and so on. So on and so forth. Okay. Now we can see that as the time passes, concentration of the reactant is decreasing. Correct? As your time increases, your concentration of the reactant A decreases. And this is the case for all reactions, whether it is zero order, first order, whatever it is. Because as time proceeds, your reactants will react to form products and your concentrations of the product will decrease. And that is obvious. But even if your concentration of the reactant decreases, will it affect the rate of the reaction? No. Why? Because for a zero order reaction, rate is just equal to K. It's a constant. It does not depend upon the concentration of the reactant. Even if with time, concentration of reactant is decreasing, in a zero order reaction, it has no effect. So here also, it will be a straight line. It will be a straight line. Okay? Now, one thing that you have to be careful of. Whenever you plot a graph, you have to understand the meaning. Okay, so let's say that you have got two options. One option is where your line is like this. Let's say this is option A. And another option is where your line is like this. And this is B. And the questioner asks you, which one is correct? Is it A or B? Now we have to understand that in both the cases, the rate of the reaction is not changing with time, and that is true. And that is true with a zero order reaction. So in that concept wise, that's right. But if you take the point 0, let's say I take this point. So this point is t is equal to 0. So at t is equal to 0, my reaction will not start. Okay? At t is equal to 0, my reaction won't start. So if my reaction does not start, I won't have a rate. Correct? At t is equal to 0, my reaction won't start. So it might start at 0.1 milliseconds or 0.2 milliseconds, whatever. So at this point of t is equal to 0, our reaction won't start and hence the rate won't be there. Hence, we cannot define a term called rate unless the reaction has begun. So, if the questioner gives you options like this, they have not asked it yet, but I'm just explaining so that you get the concept well. Among A and B, if you look, the rate is constant with time. The only difference is in trace A, in the line A, the line touches the y-axis, which means even at t, time t is equal to 0, your rate has some value, and that's not physically logical. So your correct option will be option B. Okay? If they ask. So you have to plot a straight line which is parallel to x-axis and that does not touch the y-axis. That's how you will represent. Okay? Same over here as well. Same over here as well. If they ask you, let's say this is A and let's say this is B. See, A and B are conceptually correct. But if they give you two options where there is A and there is another graph where the line looks like B, you have to opt for B. Why? Because when there is no reactant, let's say you have some vessel, you won't get HCl, correct? You should have H2 and Cl2. Then only the reaction will proceed, right? So at concentration A is equal to 0, your rate will also be not there. It won't be there. So instead of representing like A, it is more logical when you represent it like B. Okay. All right. Next, write down the heading, integrated rate equation for zero order reaction. Integrated rate equation for zero order reactions. Okay, very easy and very important as well. Again, let's take the example that we have written. Let's say I have certain reactant A, which becomes product P. Okay. At time T is equal to 0, the initial concentration that you have, okay, the initial concentration of the reactant that you have, let's say, is small letter A. Now it depends, okay. Certain questioners will put the initial concentration as A. Certain questioners will put it as C, whatever it is. You have to understand by looking at the question. So it will come through practice. Don't worry. It will come out through practice. Okay. And let's say the value of the initial concentration is A. And you don't have any products. You don't have any products. And after some time T, this reactant has reacted. How much? Let's say X amount has been reacted, some amount. We don't know. Okay, so in this case over here, it was 10 initially, 0 products. And then 2 units have reacted, 10 minus 2, and we got 8. And whatever reacted will appear over here, X. Correct? So you have to understand how this works based on stoichiometry. Now this is the case because you have got A giving P. Okay, let's say that you have A giving 2P. You have to understand the concept. Please do not mug up. You have a lot to by heart. So please do not by heart the things, understand the concept. So let's say that at T is equal to 0. This was again A and you don't have any products. But at T, sometime T, some amount of the reactant is reacted. Some amount of the reactant is reacted. And can you see the stoichiometry over here is 2P. So see the stoichiometry of the reactant is 1 and the stoichiometry of the product is P, 2P. So even if X reacts over here, it appears as 2X. Very easy. It appears as 2X. Just follow the stoichiometry. Just follow the stoichiometry. One more so that you understand. If you have A giving 3P, try it on your own. At T is equal to 0, you have an initial concentration of A and you don't have any products. And at time T, some amount will be reacted. We don't know how much that is. But then based on the stoichiometry, the amount of product that is formed is 3x. That's all. Okay. All right. Now I'll take up this. So based on this, we will learn some notations. We'll learn some notations, okay? So out of this, small letter A is the initial concentration of the reactant. Initial concentration of the reactant. In integrated expressions, you write it as concentration of the reactant initially as you put a 0 as the subscript. You put a 0 as the subscript. Okay. Now, what is X? Let's try to understand what is X. So X is basically amount reacted. Amount of reactant reacted. Amount reacted. Amount reacted. So if you have initial concentration of A and something has got reacted, what would A minus X be? It is the amount of reactant left, or it is the concentration. It is the concentration of reactant which is left. Correct? So if you look at this example, this was A, initial concentration, and then this is A minus X, which is whatever is left. So X is equal to 2, A minus X is equal to 8. X is equal to 2 and A minus X is equal to 8. Okay? I hope that is understood. Now, whatever concentration is left of the reactant is just written as A in square brackets. It is written as A in square brackets. So if I want a relationship between A naught and X based on the concentration, I can write it as, so we do know that concentration of A, that is amount left, is equal to initial concentration minus whatever was reacted. Whatever was reacted. Okay, so this is the amount reacted, or you can say that the reactant consumed, or the amount of reactant consumed. Okay. Everything is the same, just different terms. Okay, so you should know this. Whatever is left is equal to initial concentration minus whatever was consumed, X. Okay, now coming back, we have this relation A is equal to, or A giving P. We can write the theoretical rate. By just looking at the reaction, we can write the theoretical rate, correct? Theoretical rate is equal to minus dA by dt equal to plus dP by dt. Correct? It's better that you practice with concentration terms itself, minus concentration changes of A with T plus concentration changes of product with T. This is the theoretical rate. And from law of mass action, we can write experimental rate. Experimental rate is equal to R is equal to rate constant into concentration of A to the power 0, because this is a zero order reaction. Correct? Now, this is also an expression of rate. This is also an expression of rate. Correct? This is also rate. This is also rate. So we'll equate these two. We will equate these two. So what will we get? Minus dA by dt is equal to K concentration of A to the power 0. And any number raised to 0 is 1. And I'll take dt to the other side, minus also to the other side. So what I get is concentration of dA. I'm taking minus to the other side. It becomes minus K. A to the power 0 is 1 and dt. dt. Okay. So this is my expression that I have got by comparing the theoretical and the experimental rate. By comparing the theoretical and the experimental rate. Okay. Now what I'll do, I'll integrate this. I will integrate this from where to where. So we have to put the limits for integration, right? So we have a starting point. So what is the starting point of the time? Time t is equal to 0. At which, what is the concentration of the reactant? It will be, initial concentration will be A naught. And the reaction goes up to time t. And what is the concentration of the reactant at time t? It is just A. So these are the limits. Okay, now let's see what we have. Integral dx is just x. Okay. And what we have over here is integral dA. So that is going to be just A. We have integral dt and that is going to be just t. So let's put them. Integral dA is concentration of A and we have the limits. Lower limit is A naught, upper limit is A. Right? Minus K is a constant and we have T. Integral dt is T and we have the limits 0 to T. Now, how do we open or how do we apply the limits? It's always upper limit minus lower limit. So let's apply. Upper limit is upper limit is concentration of A minus initial concentration of A is equal to minus K into, you put values of T, minus T is equal to 0. So I get concentration of A minus concentration of A naught is equal to minus KT. And if I take A naught to the other side, concentration of A is equal to initial concentration of A minus KT. This is my integrated rate equation for zero order reaction. It's just like the expression that we wrote over here. See, final concentration of A is equal to initial concentration minus X. Here you have final concentration of A is equal to initial concentration minus KT. So if you compare them, see, what do you have? You have A is equal to A naught minus KT and you have A is equal to A naught minus X, which we derived earlier. See this equation, this one which we wrote over here. Correct? So when we did that, and if you compare, you can see that X is equal to KT. X is equal to KT. What is X? The amount of reactant consumed. What is it equal to? The rate constant into time. Okay, if you want, you can label the reactions as well. Let's say this is equation number 1. Let's say this is equation number 2. And you have equation number 3 by comparing 1 and 2. Comparing 1 and 2. Oh. Let's draw a graph. Let's say I want concentration of A, which is the reactant. Correct? Versus time. So this is our equation. Concentration of A is equal to concentration of A naught minus KT. So it is A versus T. So you will have A along Y and T along X. And this graph is of the form, whatever you have along the y-axis is over here. And whatever you have along the x-axis time is over here. Correct? And this is of the form y is equal to mx plus c, where you have a negative slope and a positive intercept. You should know all the patterns of y is equal to mx plus c, okay? If you have doubts regarding the same, please reach out to me. So this is of the form y is equal to c minus mx. So it means it will have a negative slope, correct? M is the slope, it is negative. It's going to be negative. And this is C, which is our y-intercept. So you can touch your line over here. And this is the y-intercept. So this is C, y-intercept. And that is going to be equal to A naught. A naught. And you have got a slope as well. Slope, negative slope, and that is minus K. That is minus K. Okay, so this is how the plot looks. So this is the reactant with respect to time. What if you want the product concentration with time? Product concentration with time. So let come back to the reaction. What is the concentration of the product that you have? It is X. So we need to plot X versus T. And what is the equation that we know? We know that X is equal to KT. Equation number 3. Equation number 3, we know that X is equal to KT. So this is of the form Y is equal to mx plus C, but then you don't have an intercept over here. So intercept is 0. Intercept is 0. Correct? So you will be having a line with positive slope. A line with positive slope whose intercept is 0. It will start from 0 because the value of C is equal to 0. And the slope of this graph is going to be K. The slope of this graph is going to be K. All right. So this is the rate, integrated rate equation with respect to the reactant. A is equal to A naught minus KT. And this is with respect to the product. X is equal to KT. Write the next heading, half-lifetime. Half-lifetime. T half. T half. You can write a definition. Now this half-lifetime will come for 0 order, first order, second order, third order, everything. So we won't be writing the definition every time. One time we'll write and then you have to register it in your brain, okay? So the time at which concentration of the reactant is reduced to half of its initial amount. Half of its initial amount is called the T half or the half-life. That is called the half-life. So how do you find the expression for half-life? We already know from the integrated rate equation that concentration at any time t is equal to initial concentration minus KT. This is the integrated rate equation. Now you have to know that the question is to find the expression for T half. So at T half, initial concentration would be the same, that won't change. The final concentration, how much will that be? The time at which concentration of the reactant is reduced to half, which means the initial concentration will become half. So this is the final concentration. This is the final concentration at T half. Okay, now let's try to put the values and try. So at T half, what amount of concentration will be left? A naught by 2. What is initial concentration? A naught, that won't change, minus K T half. Now if I rearrange this, K T half I'll take to the left. K T half I'll take to the left is equal to A naught minus, I'll take this to the right. I took this to the left. A naught by 2. A naught minus A naught by 2 is A naught by 2 itself. Correct? A naught, A naught. Now if I rearrange, what I get is T half is equal to initial concentration of the reactant divided by 2 times the rate constant. Equation number 4, important. Half-life of a zero-order reaction is equal to initial concentration by 2 times the rate constant. Please draw the graph simultaneously. Let's say I want a graph between T half versus initial concentration. T half versus initial concentration of the reactant. So what is it that you have? This is Y, this is X. So this is of the form Y is equal to mx plus C you don't have. So C is going to be 0. The value of m, slope, is going to be 1 by 2k. It is positive. So it will be a straight line passing through the origin having a slope of 1 by 2k. Okay, that's done. Now, if this concept is clear to you, try out water life on by yourself. Water life. Water life. Water life. Water lifetime. You write the definition and then you can try. Time at which concentration of the reactant reduces to 1 by 4th of the initial amount. 1 by 4th of the initial amount. Correct? So what is the integrated rate equation that we know? Concentration at any time A is equal to initial concentration minus KT. Now they have asked water life. At water life, initial concentration though won't change. The final concentration is said to be 1 by 4th of the initial, which means it is A naught by 4. Now you try it by yourself and derive the equation for T quarter, please. It's going to be concentration of A naught by 4 is equal to concentration of A naught, initial concentration minus T quarter, KT quarter is equal to initial concentration minus the final concentration is A naught by 4. If I rearrange this, I get 4 minus 1 3 times initial concentration by 4K. Equation number 5. Do not mug up the equation for water life and all. You need to know the integrated rate equation and then you can derive. It takes only 10 seconds to derive and that's fine. If you mug up a lot, if you by heart a lot, you will end up making mistakes. So no need to do that. Learn this and then you can derive. That's fine. Okay? Fine. It depends, okay? Certain people will write it as teak water. Some people will teak water. Some people do write it as T 25%. Some people write it as T 1/4. So you have to look into the words of the questions that is being asked and then you can solve your problem. Okay, so read the question very well. Next one. Completion time. Completion time. Completion time. T100 also we call it, or in certain textbooks, it's also written as TO. T completion, do you need the definition? It's clear, no? It is a time at which the reaction is complete. Okay. Time at which reaction is complete, or you can write it as time at which final concentration of reactant is 0. Final concentration of the reactant is 0. Derive the expression, come on. Concentration of A is equal to initial concentration minus K into T. Now we need to find the expression for T 100% and we know that the final concentration is going to be 0. So it is going to be 0 is equal to E naught minus K T 100. If I rearrange, T 100% is equal to A naught by K. Equation number 6. Equation number 6. Okay. Now, certain people or in certain question papers, they ask the relationship between two times. For example, if I ask you to relate T half and T 100%, how will you relate? Let's try out. Okay. So you'll get more questions so that you can increase your speed, but I'm just giving you a sample concept. We know that T half from number 4, right? Yeah, from number 4, it is A0 by 2K. T half is A0 by 2K. And from equation number 6, we know that T 100% is equal to A0 by K. Now, how can you relate it? See, this is A0 by K. This is also A0 by K. So I can write it like T half is equal to T 100% by 2. Correct? So they ask relations like this. So this is T half and T 100. They might ask you T 30 and T 70 or T 10 and T 99. We'll do that in the practice session. But now you know how to derive and how to rearrange, etc., etc. Okay. Let's draw a graph as well. Let's draw a graph as well. We have already drawn the graph. So see, when we drew the graph for concentration versus time, we drew it like this. I'll go back to that slide. This one. This one, if you remember. This one, if you remember. Concentration of A versus time. This was of the form y is equal to C minus mx with a negative slope. Correct? So here also I'm going to reproduce the same graph, but I'm just extending it. So if you can see at t is equal to 0, my initial concentration is the highest, and that is going to be my initial concentration A naught. And over here, my t value has got some value, but my y axis is 0. So here y-axis is 0 means there is no reactant left, which means this is T100 or tau. And the slope of this graph, of course, is minus k, which we have already written in the previous 2 to 3 pages back we have written. Okay. So in this zero order reaction, the line touches the x-axis where the concentration of the reactant is 0, and the point where it touches the x-axis is the completion time, tau or T100. Okay. We'll do some questions. Question number 11 of chemical kinetics. Question number 11. Let's do T half. So by the end of today's session, do make a summary chart of the zero order reactions, okay? And it will get better with practice. T half for zero order reaction. T half for a zero order reaction. A giving P is 1 hour. When A naught is equal to 2 molar. How much time does it take for its concentration to come from 0.5 molar to 0.25 molar? Very easy question. Option A, 1 hour. Option B, 4 hours. Option C, 0.5 hours. Option D, 0.25 hours. Read the question well, pause the video and try it. Okay. So see, what is the question? You have given the, they have given the T half of a zero order reaction. What is the equation for the T half? We already know T half is equal to initial concentration by 2 times rate constant. They have also given the value of A naught, and they have given the value of T half, 1 hour. 1 hour and 2 molar. So let's put that values and find something. So T half is 1 hour. A naught is 2 molar divided by 2K. So when I rearrange this, I get the rate constant for a zero order reaction, molar per hour. Correct? Always write with the units. I'll take K to the side and I'll bring R's to the reciprocal. So I get molar per hour. 1 molar per hour. Okay, I got this. Now, what is the next question? How much time does it take for its concentration to come from 0.5 to 0.25? Very easy. So we know that the rate equation is A is equal to A naught minus KT. Correct? So they have asked when it starts from 0.5 and ending at 0.25. Correct? So final concentration is 0.25 molar. Initial concentration is 0.5 molar minus rate constant is 1 molar per hour into time. So we can rearrange. You take 1 molar per hour into time is equal to 0.5 minus 0.25 molar, which means time is equal to 0.5 minus 0.25 is 0.25 molar divided by, what is the rate constant? 1 molar per hour. So molar gets cancelled. Per hour comes to the numerator and it becomes 0.25 hours. Option D. Very easy. Option D. Next question. Question number 12. A to B is an ideal gas which decomposes according to A to B gas, giving A2 gas plus half B2 gas. Okay. At start, initial pressure is 100 mm of Hg. Mm of Hg is a unit of pressure, okay? And after 5 minutes, the pressure is 120 mm of Hg. What is the average rate? What is the average rate of decomposition? Okay, this is not related to zero order reaction. This is related to average rate, which we discussed yesterday. Very easy question. They have given gaseous components, that's all. Let's try. So you have A to B and it decomposes to A2 and half B2. Correct. So initially, let's say at t is equal to 0, it is said that it was 100. So the decomposition has not begun. At 5 minutes, some part of the reactant has been consumed. Okay, so since it is in pressure, I'll write P. We don't know how much. Some of it has been consumed or decomposed. So you will get A2 whose stoichiometry is 1. So you'll get P over here. And you will get B2 whose stoichiometry is 1 by 2. So you will get P by 2 over here. Okay. So initially it was 100 mm of Hg. And at 5 minutes it is said that it is 120 mm of Hg. 120 mm of Hg. Now understand that mm of Hg is a unit of pressure for gaseous elements. So initially, if you take a beaker, you had only reactant and whose pressure is 100. But once the decomposition has begun, you have reactant and you have the decomposed products. You have the reactant and you have the decomposed products. Because everything is gaseous now. So in the vessel, you will have both the reactants and products whose pressure is 120 mm of Hg. So what can I write? Can't I write it like this? The pressure of reactant is 100 minus P. Pressure of the products is P plus P by 2. So the total pressure of all the gaseous components is equal to 120. Got it? So if I rearrange, PP gets cancelled. 100 minus P by 2 is equal to 120. So if I rearrange this, sorry, it's 100 plus P. 100 plus P by 2 is equal to 120. If I take 100 to the other side, P by 2 is equal to 120 minus 100, which is 20. And P is equal to 40. What is the unit? 40 mm of Hg. So now I have the amount of gas which is reacted. 40. 40. Correct? So what is the initial concentration? Initial concentration of A2B was 100 mm of Hg. Final concentration of A2B was 100 minus P, as we didn't know. Now P is equal to 40. So 100 minus 40 is equal to 60 mm of G. Correct? Now, what is average rate? Average rate is the changes of the concentration. A to B final minus A to B initial. This is the changes of the concentration divided by time. So, final concentration was 60. Initial concentration is 100. Divided by time is 5 minutes. And since it is a reactant, you have to put a minus ahead so that your rate is positive. 60 minus 100 is minus 40. Minus into minus 40 is 40. So you have 40 mm of Hg divided by 5 minutes. Or the final rate. Average rate is equal to 8 mm of Hg per minute. This is the answer. Okay, so the units over the concentration changes are expressed in units of pressure. That's all. Instead of molarity, it's in terms of pressure. Two questions homework. It was question number 12, right? Question number 13. T half for A giving P in brackets 0 order reaction is 20 minutes. Calculate the time in seconds. So be careful, okay? Whatever value is given is in minutes and they have asked you to give your time in seconds. So you have to convert. 1 minute is equal to 60 seconds. You will need to use that. Calculate the time in seconds at which concentration becomes 0.05 molar from initial concentration of 0.2 molar. Everything is given. You can try it. This is initial concentration. This is your final concentration. This is your T half. You have to find at which your final concentration becomes 0.05. The only thing that you have to be careful of is your time should be in seconds. So you'll have to convert your units. That's all. One more question, graphical question. Question number 14. Choose the correct plot for log T half versus log K for a zero order reaction. For a zero order reaction, very important. Try it by yourself. I'll explain it in the next section, but give it a try. So you have log T half and you have log K. Okay. Option A, your graph is like this. Option B, your graph is like this. Option C, your graph is like this. Option D. So this is A, B, C, D, all of them. All of them. Very important question. We'll do this in the next session, but then you give it a try as well, okay? Okay, so with that, we have completed the zero order reactions. Tomorrow, we'll start with first order reaction, okay? Okay, so that's all. Thank you. See you. Bye-bye.